Good afternoon or good morning in North America. My name is Gilles Gallet, and my role is a business developer in ADAS for Ansys. So just a few words about Ansys. So we are known as a global leader in simulation software, and so more than 4,500 employees, mainly engineers and PhD, working on and covering all the simulation topics, and especially all physics domain and system simulation. So we are supporting and we are committed to support our key customers and innovative customers in the major trends, and especially autonomy. And in autonomy, our primary focus is to support them in transitioning from level 1, level 2 ADAS technologies toward higher level of autonomy, where the need of simulation is mandatory. But that's already what Didier said and also Hervé said. So just to give you some global figures, so here is a nice numbers coming from IDC, and the study was published in December. It shows that the self-driving car will be deployed and will come progressively to the market. And two aspects are interesting. So level 1, 2 would be the two largest area of autonomous growth by 2024, where half of the vehicle producing that at that time would be and will have some degree of automation. So it will be mainly ADAS function. And of course, L4, L5 will remain the goal of the automotive industry, and the target and the key target for most of the key players and the chip makers, the component providers, as well as the OEM. And the development and research and development activities will continue, and this will be to prepare the ground for a massive deployment at the end of the decade. So that's the two interesting aspects to keep in mind. When we consider, when we consider the key challenges for self-driving, two are technology challenges. So of course, sensors, AI, data collections, collecting data on the road is really costly and a pain for our customers. Safety and performance is the target and the goal, and that's the reason of this massive testing requirements. And of course, the pressure for the market and the time to market pressure is also important. And most of the big players are announcing highly automated functions soon. And the NCAP is a right place to see how the deployment will come, and the NCAP is also producing a good roadmap to have this progressive deployment. And this NCAP is becoming more and more a business driver for the OEM. And of course, digital transformation is a key aspect to consider. So when we consider the safety, so safety is, as usual, linked to the functional safety, the FUSA ISO 26262, but also the cybersecurity, and main is the SOTIF. And Didier show a nice example of why the SOTIF is so important. It's so important because it requires the system to make the maneuver decision with accident risk less than a human driver. So it's like having a new driver license for the system. So, but behind this, the SOTIF is giving a methodology and approach where the objective is to give this virtual driver license through a normal use and through a definition of the operational domain design, the ODD. And this is triggering the needs for scenarios, the scenario database, the needs of envelope of testing of the different scenarios. And when we consider a system safer than the human being, the human driving, we need to consider where the system will operate. We need to consider in which condition it will operate, on which region it will operate, and then we can define by statistical approach, the quantity of scenarios or kilometers that we need to test our system against. And based on this, all the perspective, and if we consider the perspective that Hervé gave us at the beginning, he was talking about 7 billions of kilometers for testing. Of course, it's not possible on the road, and only a structured simulation, a structured methodology and approach, and a system-based methodology approach is mandatory. Most of the industry leaders have been defining some principles. So on this white paper, for example, safety first for automated driving. And this publication is summarized well the known safety by design and safety by verification or validation methods for all level 3 and more automated driving function. So the summary is required for maximizing the evidence of a positive risk balance of automated driving solution compared to the average of the human driving performance. So that means that we need to address, according to this methodology, we need to address and to make and to build a demonstration, a statistical demonstration of the safety across the known and the unknown scenarios. And this is where we need to go toward a simulation approach in order to explore the known scenario and the unknown scenario in order to cover this very large amount of testing scenarios. And this must be done each time a system is changed. So in a summary, we need to have to address the safety by validation. We need to address more than 90% of the test through validation and virtual simulation. And for 2 cases, so first for the sensor validation, which is performed mainly using data-driven and open loop simulation, which is also called reprocessing. That was also what Didier was showing. But in the same approach, feature validation is conducted through a massive data-driven closed loop simulation. And this is where we need to have a massive infrastructure for testing. And this simulation comprises several known and unknown methodology and scenarios. So the key aspect is IT, a large IT infrastructure, and of course, a simulation accuracy where we can adjust the level of accuracy according to the development stages. And this is where Ansys is coming, providing and supporting our customer with a multi-scale simulation approach in order to scale the level of fidelity according to the level of testing. So I would say at a very early stage and for feature validation, the objective is to test the features with a large amount of scenarios where we are mainly using models and not necessarily full physics models. And then we are going progressively and at different stages and during the progressively along the development in order to bring higher level of accuracy on the sensor models and on the vehicle models toward reaching a complete digital twin of the vehicle and the test. So that's the objective. And of course, at the end, the objective is to come back, to go on the proving ground, to do the final testing. And the key approach of such kind of platform is to provide a continuity of refinement of testing and a continuity of validation against the real driving and against the real testing. So when we consider the feature validation, what we call the data-driven closed-loop simulation, what we propose is to connect our simulation platform to a data ingestion platform where we can bring the collected data from the road into some logical scenarios, so pre-formatted logical scenarios, as well as by combining with the different parameters of the collected from the roads in order to produce a huge amount of concrete scenarios in the test plan. And through this automated workflow, we are applying different methods in order to strongly reduce the number of concrete scenarios. And that's the approach. And this approach makes possible to test on the HPC or on the cloud, and to have a very efficient workflow. This workflow has been implemented by Daimler, especially for ADAS level 3 scenario-based validation approach. And this approach results in a solid workflow, of course, and which consider the robustness evaluation and the reliability analysis of the different parameterized driving scenarios. In fact, it's what you see on this diagram is an implementation of the Pegasus workflow, which is the support of this safety by validation approach. And the way Ansys is reducing the number of concrete scenarios is to provide the capability to reduce by a factor of 1,000 by a combination of different methods, smart sampling methods, sensitivity and reliability analysis, but as well as neural network approach. We are able to strongly reduce the number of concrete scenarios, which make possible to achieve and to provide the proof of the validation with an optimized test plan. And then we go to the sensor fusion, and the sensor fusion is a second aspect which is key for the validation. So I mentioned already that so it's really a pain for most of the people to go on the road and to collect the data. So collecting the data is very time consuming. It put most of the vehicle program at risk, because it comes very late on the process, and the cost of such kind of approach is it can bring to very huge amount of cost. So today we consider something like between $10 to $15 per mile without the labeling, and this is the normal approach. So what we are doing today with our customer is to bring the simulation earlier on the process. So, and especially to bring the generation of synthetic sensor data earlier in the process and in a cheaper way. So for doing this, we bring our different physics of sensor, and we are covering the 4 main sensors. And these 4 major sensors are aligned in order to in front of the different use cases. So, for example, at a component development level, which is more for the tier 1 and tier 2 suppliers, they can apply Ansys at very detailed simulation of physics for example, for radar antenna, or for a camera or a LiDAR, for the optical aspect, the thermal aspect. So all this aspect can be simulated in very detailed physics. And then we reduce the physics in order to solve different level of new use case in the vehicle integration approach, where the implementation of the sensors on the vehicle influence drastically the performance of the sensors. So by simulation, again, based on the CAN model of the car body, it makes possible for an antenna, a radar antenna, to compute the installed performance of the antenna on the car fascia, for example, and same for the different sensors. And then we bring, again, these models into open loop or closed loop simulation for perception and fusion testing of sensors. And in that case, when we are talking about synthetic sensor generation for the different scenarios, we consider two approaches. One is the open loop, and for the open loop, we consider the sensor validation based on a data-driven open loop simulation approach, which is also called a reprocessing. Such kind of simulation can also be used for machine learning as well. And then we can go on the closed loop simulation, where it's mandatory at system level to test or to validate the sensor fusion, as well as to implement the worst case scenarios. And in that case, the physics sensors are interested in order to have the full stack in the testing. So we can address the non-real-time software in the loop, as well as real-time software and hardware in the loop. On the bottom, you can see an example with a radar, starting from the antenna on the air. Then we compute the antenna pattern as installed on the car body. So we can consider the different aspect of the implementation. And then we can go to open loop scenarios with the full physics. And here you have a nice scenarios with 6 radar, all computed on the driving scenarios. It's computed fast. And then we can go to real-time closed loop scenarios where it makes possible to achieve strong real-time with different scenarios. So that's the way we are covering that. And then when we are talking about hardware in the loop, the question is, why do we need physics for testing hardware in the loop? The reason of physics is because you need to address different worst cases or rare cases or corner cases. And for a camera-based ADAS, the nighttime driving is quite complex for several reasons. But the first reason is because what you see on a camera is light. So it's an illumination of an object, which can come from your headlamp or which can come from different light. And then this transformation of light into a different an image is done by an imager, which react also to the physics. So all these aspects can only be done considering the physics of simulation of the light. So that's an example for the camera. And then we need to bring this or these physics-based sensor models inside the hardware in the loop bench. And to do so, we are partnering with key players. So we are partnering with NI and OPAL-RT, of course, and combining Ansys simulation, physics simulation with NI, and we can let system integrator like OPAL-RT to have a complete system integration considering the Ansys models inside the closed loop simulation environment. So this is the way we are approaching. And here you have an example which has been built by OPAL-RT. So this is a test bench with an OPAL-RT platform where it makes possible to inject inside the ADAS ECU. So here in this box, you have the ADAS ECU where we can inject a full physics images of the camera, and then we can put the ECU in exactly same mode as is running on the vehicle. So the ECU is not running on a hill mode. The ECU is running on the vehicle mode, where it makes possible to test the corner cases. So in that case, and the video that I can show you is an example with the Mobileye IQ. So the Mobileye IQ is on the bench. So the Ansys VR experience is producing the image, stimulating the IQ. The IQ is then applying the perception and detection, and then stimulating the ADAS function. In that case, is for testing the I-beam assist function and for testing the I-beam assist function in a repetitive way. So it makes possible with such kind of bench to have a complete reproduction of different testing very in a systematic way. So in a short summary, such kind of benches that we can propose with OPAL-RT is to bring complete robustness testing of a camera-based function on hill, and which make possible to replace 80% of the road driving testing by a virtual validation. And this approach has been validated with different OEMs and suppliers. And we have the confirmation that it makes possible that we can produce synthetic field operation test data very early on the process. And then it makes possible to do the final robustness testing on the hill camera-based platform. So all the camera-based function can be tested on the hill. And then it also enhances, of course, the process in between the OEM and the suppliers, making possible to exchange models during the development process in order to create this digital twin along the development process, and not to discover the issue on the road when the car is released. So that's really a new innovative approach that we are proud and pleased to propose. Thank you.
Thank you very much, Gilles. That was an excellent presentation, very detailed.